Hey, welcome to week 13, the ACT Math Prep course. We're going to be talking about circles today. So basically everything circles you're going to need for the ACT. So remember, a circle is just all points that are the same distance from a center point. So it's just a collection of points, okay? All points, we say equidistant. That just means the same distance from a center point. All right, so what are we talking about here? We've got this center point, right? So we've got this point, and then I mark this distance right here, and I draw a point. And I mark the same distance, and I draw a point, and I do the same thing. And what happens is I start to build all these points that are the same distance from the center point, and although my picture doesn't look like it, we develop this almost, it looks like a curve or a line, but it's not. It's actually just a bunch of points, but we call it a circle. Okay. The things you need to know about the circle is this distance from any point on the outside to the center is called the radius. Okay. That's one of our big definitions that you got to know. It's the distance from the center of the circle to any of those points on the circle. Okay. And a big star here, all radiuses, it's actually radii are equal in length. They're all the same. This one is 5, if this one is 5, if they're all 5, if one of them is 5, they're all 5. So that's one thing they're going to expect you to know on the ACT is that all the radiuses are equal in length. Okay? So first of all, just some basic definitions that you probably know, but we got to make sure that we talk about them at least briefly. These formulas that go with circles. Okay? So the first one is the diameter. Okay? The diameter is 2 times the radius. And if we draw a picture here, the radius is this distance here from the center to the outside. The diameter is just the distance all the way across. So the diameter goes from here all the way over to the other side. So it's just twice what the radius is. Another way to think about this is that the radius is half of the diameter. Okay, those are pretty basic. You just double the radius to get the diameter or cut it in half to get the radius. So that's the first definition. The next one is circumference. All right, circumference is basically the distance around the outside. It's the perimeter of the circle, if you will. It's gets a special name just because circles are special. And the formula is that the circumference of the circle, the distance around the outside, is 2 times pi times the radius. Okay. Now, alternately, you can connect these 2r, right? 2r is just the diameter. So what you can do is you can say, oh, well, really, that's just pi times the diameter. Okay, so that's an alternate form there. But usually we're used to using this one, 2 pi r. The circumference, the distance around the circle, is 2 times pi times the radius. Now remember, if the radius is 4, a lot of the times we'll write 2 times pi times 4. We'll actually multiply those numbers together and leave it as pi. Sometimes we use 3.14 for pi, and sometimes we just leave it as pi. A lot of the times on the test, it's left as pi. So just be aware that that's okay to do. It's okay to just leave it in terms of pi is how they say that. Okay, and the last formula we're going to use is the area formula. The area of a circle is pi times the radius squared. Okay, it's the one with the squared. And it's easy to remember, area is a square measurement, meaning it's in square feet or square meters. It's an area. So we talk about area in terms of squared units. So it's easy to remember that area is pi r squared. Okay. All right. So those are the basic formulas you just got to kind of put to memory there. Now let me talk about a few things, a few definitions, if I will. So here's some definitions that you got to know. First of all, when we have a circle with a center point, we define this angle that's set at the center, right? This is called a central angle. It's easy to remember because it's in the center of the circle. So that's, of course, why it's called a central angle. Okay? It's this distance from here to here. That angle that we sweep across, that's a central angle. Okay? The next thing you got to know is when you have one of these central angles, okay, it defines what we call an arc. An arc is part of the circumference. It's just a little piece of the outside. Okay? We call this an arc. Okay? And the third definition you got to know is the same thing. You've got the central angle. But now I want to talk about the area of this piece. So it's part of the entire area, but we call it a sector. Okay? Sector is just one little piece of the circle, part of the area. All right. So what's kind of weird is that arc can be described as far as a length, and we'll talk about that in a little bit. We can measure that arc. I can like use a ruler or a curved piece of string, and I can measure that distance. But also, I can call this arc in terms of a degree measure, which is it kind of seems weird, but the arc measure in degrees. Okay. The arc measure. When they say arc measure, they're not talking about the length of that arc. They're talking about the measurement of it. It's equal to the central angle. Okay, so what I mean is if I've got a circle here, let's say this is a 90-degree angle as a central angle. That means this arc measure, okay, I'll call this A and B so you can kind of see what I'm saying. The arc measure of AB is 90 degrees. So whatever the central angle is, if it's 90, the arc measure is 90 as well. So in the same sense that 180 degrees is halfway around the circle, that arc measure would be 180 degrees. So sometimes we talk about it in length, that's arc length. But when we talk about arc measure, we're basically talking about the relationship between the central angle and this arc measure of the arc, okay? Just something you gotta be aware of there. All right, so we were talking about arc length. We wanna actually be able to measure the length of an arc at actual distance, okay? And remember, arc length is basically a fraction of the circumference. Okay? This is a really easy way to think about it, a fraction of the circumference. That actually gives you the formula if you think about it like this, okay? A fraction of the circumference. Well, the arc length is equal to a fraction, which is the part over the whole, right? What fraction of the circle are we talking about? Times the circumference. Okay, now let's look at an example because this could be kind of weird to think about. Just by looking at this formula, it might not be obvious. All right, so let's say if the radius is equal to 6 and the arc measures 55 degrees. Okay, so that means that central angle is 55, and so we define that arc measure to be 55 degrees. The question is, what is the arc length? Okay, so we're going to use our formula. The arc length is equal to the fraction of the circumference. So like what fraction of the circumference are we talking about? Times the circumference, okay? Now remember, off to the side here, I'm going to remind you that 2 times pi times r, that's the circumference, okay? That's the formula. So what is the fraction of the whole circle we're talking about? Well, we're talking about 55 degrees, right? So just put 55 degrees out of the total number of degrees in a circle. If you think about a circle, it's all the way around, that's 360 degrees. So there's the fraction that we're talking about, times the circumference. So 2 times pi times the radius, which in our case is 6. So this is going to give us the arc length. It's the fraction out of the whole. So it's always the arc measure out of 360, because 360 is the total. So the part that we're talking about is 55. So 55 out of 360 times 2 pi r. I'm going to get out my calculator for this, and I'm going to say 55 out of 360. Okay, that gives me the fraction. So that's the decimal representation. Times 2 times pi times r, and the radius was 6. Now this gives me a decimal, 5.759. Okay, so I could definitely use that. What was it again? 759. 5.759. Now, alternately, they might leave the answer in terms of pi. If you look at the answer test, the answer booklet on the ACT, it might have it say blah, blah, blah pi, a number of pi's. Well, in that case, you don't really use the pi here as 3.14 or pi like I used on my calculator. I actually use the pi button. What we do is we just put the pi at the end. So we want to say, what is 55 divided by 360 times 2 times 6? That's the number, and then pi will just go at the end. So you just stick the pi at the end, you do the rest of the math, And you say, well, that's the number of pies. So what I want to do here is I want to do 55 divided by 360 times 2 times 6 gives me 1.83. So that's the number of pies. So 1.83 pi. So either one of these answers would work. They're the same thing. If I go back to here and I do this times pi, right, what is 1.83 times pi? Well, I don't know. Let's figure it out. All right, there's 1.83 times pi, and of course it's going to give me the same thing, that 5.75. So they are the same thing. One of them just is in terms of pi, and that's very, very common. So there you go. That is the idea behind that question. All right, so let's look at another example here. In this example, the question is, what is the radius, okay, of a circle that has a 135-degree arc that measures 48 pi. So let's say we've got this arc, okay, we got a circle, we have this 135-degree arc measurement, right? Remember, that means that the central angle was 135 degrees, so this is 135 degrees. And somebody tells us that this length, the arc length, is 48 pi. The question is, what is the radius? Okay, well, we're going to use the same formula that we did last time. The arc length is the fractional part of the arc. So what fraction of the whole arc, or what fraction of the whole circumference are we talking about? Times the circumference, so times 2 pi r. Well, let's think about it. We know the arc length is 48 pi, so we can fill that in for L. We know the part, it's 135 degrees out of the whole, which is 360 degrees, times 2 times pi times the radius, and we're just going to solve for r. Okay, so basically what I have to do is find out what all this stuff is. And I'm going to leave the pi, okay, because you're going to see pretty soon when I divide the pi out, the pi's will cancel on both sides, so that's okay. All right, so let me get my calculator here. I want to do 135 times 2 divided by 360. Okay, so I'm going to calculate this. I get 0.75. So what this simplifies to be is 48 pi equals 0.75 pi times radius. Okay, so if I divide both sides by 0.75 pi, I will have solved for the radius. Okay, notice how the 0.75 and the pi both cancel and leave us with r equals. Then all I got to do is see that the pi's cancel. That's convenient. I just need to know what 48 divided by 0.75 is. So I get out my calculator, 48 divided by, I'm going to just do second answer because see how I already have that 0.75 as my last answer? 48 divided by answer will do it. And second negative is answer, so that gives me 64. So that means the radius was 64. Okay, so I can solve both parts of that equation. Anytime you have an equation with two parts, you can solve for either one. I suppose alternately, I could solve for the part. It could say, what's the arc measure if the arc length was this and the radius was this? So I could solve for the part, right, times 2 pi r. Really, I could solve for any of these variables that are in there. The arc length, the part, or the arc measure, in other words, or the radius. You can solve for anything. As long as you know the other two, you can solve for that. Okay. All right, so now we're going to talk about sector area. So the area of one of these sectors. So just a quick reminder, we've got the central angle, and it forms what we call a sector. So we're just going to be able to calculate that area. So the formula basically is that the sector area is just what fraction of the circle are we talking about. So the same thing as arc length. It's the part over the whole. What fraction of the circle are we looking at? Times the area formula for a circle. And just a quick reminder, area is pi r squared. So basically what it comes down to is the part over the whole, the fraction of the circle, times pi r squared. Okay, so let's look at an example. Let's say that we've got a circle with a 120-degree central angle. Okay, it's the angle from the inside. Got a 120-degree central angle, and we know that the radius of this circle is 12, okay? So what we do is we say, okay, the sector area is the part over the whole. Well, we're talking about 120 degrees of the total 360. So that's my fraction. It's 120 out of the 360 times pi r squared, okay? So again, we can always answer this thing in terms of pi, or we could go ahead and put the pi in there. First, I'm going to do it without actually calculating it with the pi. So I'm going to do 120 divided by 360. That's going to give me the fraction. So that's a third of the circle times 12 squared. So I'm going to raise that to the second power. That gives me 48. So if I think about this thing should be 48 pi. That's the area of that sector. Okay. Now, of course, if your answers are in decimals, if they say round to the nearest decimal, you just either multiply it by 3.14, which usually is all you need, or you could take that 48 and multiply it by actually using the pi button, which is the second caret. You see it here in the blue. That'll give you a more precise answer, but it's, you know, really pretty much the same thing. Although, if we were rounding to the first decimal, this answer would be wrong. This 150.72 would be wrong. So maybe it's best to use the actual pi button there. Okay? All right. So that's a basic question where we're finding the sector area. So let's try something else here. What if it says find the central angle? Okay, another example here. Find the central angle if the radius of the circle is 10 and the area of the sector is 50 pi. Okay, so this is a prime example of what we were talking about. Here's my formula, the part over the whole. We always know the whole is 360, so I guess I could put that there. Times pi r squared. Okay, so we know the area of the sector is 50 pi, so I'm going to fill that in for S. The part is what we're actually looking for here. We're looking for that central angle times pi r squared. All right, pi r squared. 100 is 10 squared, so 100 pi would be pi times 100 squared, times the part that we're looking for over 360, and that equals 50 pi. Okay, so basically I just need to solve for p here. So I'm going to divide by 100 pi, divide by 100 pi. Remember the pi's cancel here. So that leaves me with 50 over 100 equals p over 360. Then all I have to do is multiply by 360, and that's going to get rid of that 360 and have me solving for p. So this is going to be my answer. I just need to calculate what it is. So 50 divided by 100 times 360, and it's going to spit out my answer of 180. Now remember, we're asked for the central angle, so we know that this is a 180-degree angle that makes the certain sector area with the certain given radius. So 180 degrees is our answer. Okay. So again, they can ask you for any of these things that could be unknown. They could give you the S and the P and have you find R. They could give you the P and the R and have you find S. You just have to be able to be flexible with knowing how equations work. Okay. All right. So let's go back to this central angle and this arc measurement. Okay. So central angle and arc measurement, or just arc measure for short. Okay. So what we've got is we've got this central angle here. All right. And let's say it's 80 degrees. Okay. Now, I always think of this like a slingshot, right? If you pull from that central angle, you pull that angle back in this direction and you land on the circle. Okay, what that's going to look like is this. These two endpoints didn't change, right? We'll call this A and B. If you leave the A and B alone, but you pull that angle back, now you're on the circle, okay? To any point on the circle. It actually doesn't matter where on the circle you are. What happens is this angle gets cut in half, okay? This angle that was 80 degrees now becomes a 40-degree angle, okay? And I'm going to define this for you. This is called an inscribed angle. It is inscribed inside the circle, okay? So basically the inscribed angle is always half as much as the arc measure. And since the arc measure, right, we measure this arc here, since the arc measure and the central angle are the same, then it really just means that the inscribed angle is half of the central angle. It's because, remember, we said the central angle and the arc measure are the same thing. These two are the same, so that means that the inscribed angle is always half. Or you can think of it as double. The central angle is double the inscribed angle. And we'll look at some examples here. All right, we'll do a lot of examples here. All right, so let's say this measures 130 degrees, this arc measure, okay? Now remember what that means again is just that that central angle is 130. But as soon as I pull it back, and let's pull it back over to the side here, because it doesn't really matter. But I take that angle and I pull it down to the side, and now I'm looking at this angle here. Okay, what is the measure of that angle? Well, it's half of the central angle. So it's 65 degrees. That little angle there is half. All right, what if they give you the inscribed angle? And they say, oh, this is a 74-degree central angle. What's the measure of this arc? Well, the measure of that arc would be double 74. So it'd be a 148-degree arc measure. And just remember what that means is that this central angle is 148 degrees, because these are the same thing. The measure of the central angle is the same thing as the measure of the arc, okay? That's how that relationship works. All right, so one thing you gotta know is that the sum of all arcs in a circle, you add up all the different little segments, it's gonna equal 360 every time. Okay, if this arc measure is 30, and this arc measure is 150, that means that this one has to be 180 degrees. Okay, I mean, just think about where it comes from, right? It's saying the central angle is 30, this central angle is 150, this one has to be 180 because they have to all three add up to 360 because the interior of a circle always adds to 360. That's all that's saying, okay? You just got to know the sum of those is 360. Now here's how they'll do it. They can do things like this. They'll say the arc measure is 3x and this is x plus 15. Well, you know that these are the same. So you set them equal to each other and you solve for x, okay? Or maybe they say, you know, we've got this central angle that's x plus 10 and this inscribed angle is x or 2x minus 15. Well, you know that x plus 10 is 2 times this 2x minus 15. There's your equation. The big angle is double the little angle, okay? Or you can say half of the big angle is equal to the little angle. Either way that works, but you just got to know that relationship and how you could set up an equation, things like that. Okay, also with the knowing the sum of the arc measures, you could be given something like this. You could say this is 85, find the measure around here. Well, you just do 360 minus 85, okay? Because the total should be 360, you've already used up 85, so you take that away, it gives you the remainder. A little bit harder of a problem would be something like this. This is x, and from here to here is x minus 14, or let's say plus 14, and from here to here is x plus 16. Find x. Well, you just say that x plus 16 plus x plus 14 equals 360. They should all add to be 360. There's an equation that you could solve to find x, and then, of course, answer the question. So those are all a slew of things that they could ask you when it comes to arc measures and inscribed angles and all those things. But those are definitely problems that are pretty common on the test. All right, so now here's this idea of shared vertices. Okay, Remember I said when you have this central angle like this, you can pull it back to anywhere on the circle. What's crazy is I can pull it back to right here. It's not really pulling it back, but it's pulling it off to the side. But if I look at the measure of this angle right here, that's kind of hard to see. Maybe I'll draw this in a different way. I won't go so extreme. Let's say I pull it off to the side here, okay? If I look at this angle, you see how it's still this central angle, but then moved to the side. It can be moved down or to the left or to the right or anywhere. It still forms this angle. That angle is still half, okay? So I'm gonna use a different color here. I'm gonna use this light blue. This measurement of this light blue is half of this central angle with the little blue arc, okay? As long as you move it to the circle, it's half. It doesn't matter where I pull it to. So what that means is if I don't care where I pull it to, this should be the same angle as the first one, right? I pull it to the circle, this angle and this angle should be the same. And they are. As long as they share vertices, as long as these 2 points A and B are the same for these two inscribed angles, they'll be the same. So what you can say is any inscribed angle is equal to any other inscribed angle as long as they share the two vertices, these 2 points up top that I'm bringing across. So what they could do is they could say, okay, let's fix this A and B, and let's look at these two inscribed angles here. We'll call this angle C, call this angle D. What do we know? We know that angle C is equal to angle D, okay? Because they have the same vertices. When I pull them back, they have the same location. So what they're gonna do is they're gonna say things like, all right, maybe this is x minus 60 and this is 4x plus 1. Find x. Well, if you know that they have the shared vertices here, then you can say that these two are equal to each other, okay? That's definitely something they could ask you. They'll utilize that information in different ways on test questions. All right, so what we've been talking about is if we have two vertices, right, and I bring it back to here, or I bring it back to here, what I'm saying is these two angles are equal, okay? Now, if you drew a line from one vertice to the other, you notice how I pull back to the same side of that line? If you're on the same side of this imaginary line, then yes, this angle will equal this angle. But if you're on different sides of this, meaning one of them is here and the other one is here, then it doesn't work like that. You see how they're on different sides of the imaginary line? Okay, one up here, one down here. When they're on different sides, they're actually supplementary. So if we call this angle D, and we call this angle C, we're going to say that angle C plus angle D actually equals 180 degrees. So these two are now supplementary, okay? If they're on the same side, they're equal. If they're on different sides, they're actually supplementary to each other, okay? These two inscribed angles. All right, a few special cases. So here's some cases that are sort of special, but deal with the same idea, okay? All right, so here's what we got. Let's say we have a diameter. Oh my gosh, that's a horrible looking diameter. Let me try that again. Here's a diameter. Remember, diameters go through the center of the circle, okay? If you have a diameter, of course, this central angle measures 180 degrees. So if I pull back to anywhere on the circle, what's the measure of that angle going to be? Well, it should be half. So it's 90 degrees. That means it's a right angle. So if you have a diameter that you have an inscribed angle, it will always make a 90-degree angle. So the inscribed angle is 90 degrees if the diameter is the line going across, okay? If your central angle is 180, you bring it back to 90 because that's half. But really, you just need to remember if it's a diameter, you have a right angle here, which means I have a right triangle. Anytime you have a diameter, this is a right triangle, okay? So you could do things like Pythagorean theorem, a squared plus b squared equals c squared. You could use sine, cosine, and tangent here because we have a right triangle. There's all sorts of things you can use. But it's just really important because this one I see a lot. This one's one of the more common ones where you talk about these inscribed angles. They give you a diameter, and it seems like they don't give you any other information, but there's a lot you can get. You know, the angle, you know, Pythagorean theorem holds, all those things. All right, so another special case. Let's say here's my two vertices, and my central angle is let's say 80 degrees, okay? We'll say the central angle is 80. So if I bring it back to here, that's 40. If I bring it back to here, that's 40. Basically, if I bring it back to any point, I'm making a 40-degree angle. Well, what if I sort of do this weird thing here where I bring it back to itself? I know that's kind of a weird idea, but if we call this a tangent line, it actually still works. This is still a 40-degree angle. So you'll see this, and it looks really weird. You'll see this tangent line coming off and this line here, and they'll say things like, what is the measure of this arc? Well, if you know that this angle is 60 degrees, this is now an inscribed angle, right? Because it's all the vertices are on the circle. That means that the arc has to be double that. It's 120 degrees, okay? Same thing, when you extend it back, you get double. So this one's the strange one. This is when you're dealing with tangents, but it works the same way. This is an inscribed angle. So when you're talking about what is the arc, it's double, okay? This one's funky looking, but you gotta remember it's the same exact thing, okay? All right, so while we're on the subject of tangents, let's maybe define that for us, okay? A tangent is a line that intersects a circle one time. And only one time, actually. It can't hit it more than one. So a line that intersects a circle only once is what we call a tangent. So if I've got a circle here, this is not a tangent line because it intersects it twice. This is not a tangent line, it doesn't even touch it. But when I look at this line right here, it just barely touches it for a half second. This is a tangent line. Okay, the one that hits twice is called a secant line. So here's what you got to know about tangent lines. All right, this is a tangent line. Tangent lines are perpendicular to a radius. Not any radius, of course, but just one specific one. The one that comes right down and touches the same point, whatever radius touches this tangent point, forms a 90-degree angle with the line, okay? This is huge. They will ask questions about this for sure on the test. They expect you to know that tangent lines are perpendicular to these points of tangency. That's what we call this point, is a point of tangency. This radius that intersects at that point is perpendicular to this line here. Just gotta put this to memory. When I see a tangent line, I immediately draw a radius and draw that perpendicular, or that 90-degree symbol. First thing I do. If I see a drawing and they say, this is a tangent line, I go, okay, well that means that radius there is perpendicular. First thing you do, okay, when you come across these problems. Because that's what they're trying to imply. It's almost always what they want you to get from that. Okay, now let's look at two intersecting tangents. So let's say we've got this tangent line here, and we've got this tangent line here that's supposed to intersect at one point. Okay, these are called intersecting tangents. So if you have two tangent lines that intersect, we have intersecting tangents. Here's what you need to know. First of all, obviously it forms a 90-degree angle with one of these radiuses, okay? The other thing you have to know is that this length and this length are actually equal. So the length from this point of tangency to the intersection point is the same as this intersection point to that point of tangency, okay? If I call this line segment AB and this one is CB, I would say that line segment AB is congruent to line segment CB. They are equal because they are intersecting tangents. That happens. Next thing you got to know is if I connect the dots here between these two, all of a sudden I have two congruent triangles. That black one and this blue one are congruent, okay? This makes two congruent triangles. And remember, we haven't actually talked about it yet, but congruent means same size, same shape, everything's the same. So that means this side and this side are the same length. It means that this angle and this angle are equal. It means that this angle is congruent to this angle. So it's kind of like an angle bisector. Everything in those two triangles are the same, okay? All right, so those are the two things that you have to know. Let's look at an example of how we could use that information. Okay, so let's say we've got a circle And we've got this tangent line here that intersects this line between the center of the circle. Okay, so if the radius equals 7, find the length of the tangent segment. Okay, first of all, this radius here is the same thing. It intersects at a 90-degree angle. And if this radius is 7, that means this radius is 7, right? All radiuses are the same length. So the question is, let's pretend this length was given to you as well. So the question is, what is the distance from here to here? You know that from here to here it was 5, and you know that from the radius was 7. Well, this is just Pythagorean theorem, right? A squared plus b squared equals c squared. The reason we know that is because it's a right triangle, because we know that that tangent line is perpendicular to that radius. So I would say a squared plus b squared equals c squared. Now where do I get 12? I just add those two lengths together. I'm not going to solve this, but that's the idea of how that information could be used on a test question. Okay. Yeah, so also if you've got an inscribed circle, inscribed means written inside. So that would mean like I've got this triangle here, and let's say it is inscribed by this circle. Wow, that's a beautiful drawing. Thank me later. So let's say it only hits once here and hits once here and hits once here. What that means is you've got these 90-degree angles from these radiuses. So just remember that if something is inscribed, these are a bunch of tangent lines. Okay, because it's inscribed, this is a tangent line, so is this one, and so is this one. These are all 3 tangent lines because they're inscribed. The circle is inscribed inside of the shape. That means that we've got tangent lines. Okay? All right. So here we go. Let's talk about chords briefly. There's not a lot of stuff on chords, but I've seen a few things pop up, and I just want to mention a quick few little things. A chord is basically any line segment that has 2 endpoints on the circle. So it could be anything from any 2 points on the circle. That's a chord. This is a chord. They're all chords. Anything with 2 endpoints on the circle. One thing you got to know is that a chord that goes through the center is given a special name. That's the diameter. Okay? A chord that goes through the center is the diameter. Now here's the things you got to know about chords. If you have 2 chords that are equal length, meaning this is the same length as this, what that means is these little sector areas, and that's not really the name of them, but I'm just going to call them these little, maybe we'll call them chordal areas. Those 2 areas are equal. So this and this are equal areas, as long as the chords are the same length. Okay? Same thing about arcs. These arcs that are defined here are the same length because those chords are the same length. Okay? That's one thing you got to know. And then secondly, if you have a chord that is a chord that is perpendicular to a radius. And let me draw a picture of that. If you have a chord that is perpendicular to a radius. So here's your radius, and here's your chord. Okay, if this is perpendicular, right, if it meets at a 90-degree angle, what that means is it bisected it. Okay, that means the left half here and the right half here are the same length. So if you have a chord that's perpendicular to the radius, you know that it's bisected. And the way I've seen it is like you can make triangles out of this and you start talking about area and things like that. But you just got to know that those 2 little things, there's not a lot on chords, but those 2 things have popped up a few places, so it's good to know. All right, now let's talk about the equation of a circle. Okay, so here's the general formula. X minus h squared plus y minus k squared equals r squared. Okay, now h and k, these 2 letters, are the center of the circle. H and k are the center of the circle. It's that location in the middle. R is the radius. Okay? Now, 2 things that trip people up all the time. If you notice in the formula, it says x minus h, and this is just h. That is like having a negative h in the formula and just a regular non-negative h in the center. So they're different signs, okay? So if you have something like x minus 4 squared, that means that h is 4. Not negative 4, but 4. They have to be opposite signs. If the formula has a negative, you're always going to have an opposite sign. Now, what if in the formula it says x plus 4? Well, that means that h must be negative 4, because you're really doing x minus h. And h is negative 4, to where these double negatives make a positive in the formula. Okay? The other thing that can trip people up is this is not r. Oh, you can't see it, can you? Sorry, I can realize that you just can't see that. Already here. This part on the right side of the formula is r squared. It is not the radius. It is r squared. The radius is just r. So when you see equals 49 over here, that does not mean that the radius is 49. It means that the radius is the square root of 49. Because it's r squared, and to find r, you square root it to make the square go away. And that, of course, is 7. But a lot of the times, this number won't break down to a nice, pretty even number. But just something to be aware of there. The h and k are always opposite of what you see in the formula. And if you're writing the formula and you know the center, you better write them as opposite numbers. And in the formula, it's r squared on the right side, not r. So if you see r squared and you see that it's 100, remember that the radius is 10 because it's the square root of 100. Or if you're given the radius and you're writing the equation, you've got to square it to write the equation. Okay, those are the two things that are going to trip up a lot of people. Okay, so let's look at an example. All right, find the equation of the circle with center 3, negative 6, and radius equal to 12. Let's do diameter equal to 12. Okay, so you've got this center point here, and you've got this diameter. Well, first of all, the diameter is 12, which means the radius has to be 6. So there's the first thing that might trip you up. So the radius is 6, and the center is 3, negative 6. Well, here we go. X minus h. Well, h is 3, so we get x minus 3 squared. Plus y minus k. K is negative 6. So when I actually write that, it's going to be y plus 6 squared. Equals the radius squared. So the radius squared is 36. And this is going to be our equation. X minus 3 squared plus y plus 6 squared equals 36. So just look at it real quick. Make sure you really get this. 3, positive 3 and negative 6 make a negative 3 and a positive 6 in the formula. And if radius is 6, you'll see a 36, which is the radius squared in the formula. Okay? Easy to get those messed up. All right, so if what is r? So what is the radius and what is the center if the equation is x plus 1 squared plus y squared equals 10? Okay, what's the radius first of all? Well, remember 10 is radius squared. I wrote a little equation there. 10 is radius squared. So that means if I want to find the radius, I've got to get rid of the squared. So I square root both sides. Square and the root cancel. They leave me with the radius is the square root of 10. That is my radius, the square root of 10. Now what is the center? I see a plus 1 here. That means I should put a negative 1 here. It's x minus that. Now notice here there's nothing here. It just says y squared. But you have to recognize that y squared is the same as y plus 0 squared. So that means my k is 0. So that's another tricky thing here. There's my radius and my center. If you see x squared plus y squared equals 100, then your center is 0, 0, and your radius is 10. So there's another quick example of when you don't see that x plus a number squared, when it's just x squared and y squared, it's still a circle, it's just centered at 0, 0. Okay? All right, finally I want to do a little flow chart here of what circles will look like versus ellipses versus hyperbolas. Okay, you're not going to be asked a lot about these, but you could be given a few questions about these. So first of all, let's look at circles. Okay, so circles look like this. X squared plus y squared equals 4. Okay, an ellipse would look something more like this. 3x squared plus y squared equals 4. Okay, now hyperbola would say 5x squared minus 3x squared equals 4. Okay? This is one way you can see them. There's lots of different ways to write these, but I just want you to see a couple different ones. So notice a circle, right? This number and this number are the same. They're both 1. Over here, these are different. There's a 1 and a 4, or 1 and a 3. So if the numbers in front of the x squared and y squared are different, you don't have a circle anymore. You have an ellipse. Now in hyperbolas, these numbers could be the same or could be different, but the main thing is this negative sign. When you see a minus x squared minus, sorry, this should be y squared. When you have an x squared minus a y squared, you're looking at a hyperbola, okay? Ellipses and circles look the same. They both have pluses. But in a circle, these numbers are the same, whereas in an ellipse, these numbers are different. So an ellipse looks something like this. It's like an elongated circle, whereas a circle is completely round, like that. Just so you know, hyperbolas are kind of like this. They're kind of strange. All right, an alternate way, if maybe it wasn't centered at 0, you would see something like this. Okay, but again, it's like the number in front here is a 1, and this number here is a 1. Whereas with an ellipse, you would see 3 times this plus 7 times this. So these numbers being different mean that you've got an ellipse versus a circle. Now finally, in a circle, you could have a number in front, but it would have to be the same number. As long as these numbers match, we're good to go. Now in an ellipse, you could have something like a fraction, actually, x squared over 5 plus y squared over 2. This is kind of like 1/5, and this is kind of like 1/2, because there's a 1 in front there. So again, those numbers don't match. If it's a plus, you're an ellipse. If the numbers are the same, it's a circle. And of course, if there's a minus sign, then it's a hyperbola.
All right, so the last thing we're going to talk about is ratio line problems. All right, so what it is they give you this line, and they'll label these points, you know, A, B, C. Sometimes you have more, D, E, and F, whatever. But here's the thing. They're going to give you like a ratio. So they'll say the ratio of AB to BC is 3 to 1. Okay, so what that means is whatever length BC is, it's 1, and the length of AB is 3. That's one example, because that's the ratio 3 to 1. But it doesn't have to be 3 and 1. It could be that this is 2, and this would have to be 6. That's still in the ratio of 3 to 1. Okay, there's 3 parts for every 1 part. There just happen to be length 2. This could be 10, and this would have to be 30. Okay, so when this happens, we don't know what exactly A, B, or BC is, but we know how they're related. So when that happens, we want to use a variable to represent the length. Okay, so we'll call this X, and then we'll call this 3 times X. Okay, that's kind of the main idea here. That's the first starting idea. Okay, so one thing you got to remember to do is to write all ratios with variables. So you want to introduce some variables, and I mean variables are important because they help us set up equations, okay? All right, so you want to try to write all segments in one variable, if possible. Meaning, you don't want to introduce another variable, like if this length here is something else, you don't want to call it y unless you have to. The reason you would call it y is because maybe there's no relationship between BC and CD, or AB and CD. If there's no relationship between this segment here and the other segments, you got to just sometimes have to call it another variable. But as an example, if let's say that we knew that BC was congruent to CD, then we could call that X, because it's the same as that other one, which is also X. So we want to try to write it in one variable if possible. Sometimes you can't help it, but write it in 2 variables. Okay, then the whole point of using these variables is we want to set up an equation. Sometimes you'll have more than one equation too. So you want to set up equations with those variables that we can solve. Okay, Then, of course, you want to solve and then answer the question. Like, what are they asking for? Are they asking for the length of one of the one of the segments? Or are they asking for the variable x or y, or what are they asking for? Okay. Now, one thing to remember here is that guess and check is a great option here. Okay. You can plug in those given values from the answers, right? If they give you A, B, C, D, E, you can plug in, you know, if they say, oh, the length is 7, well, you can plug it in and see if that makes sense. See if something breaks down when you do that, or if it all makes sense. If it makes sense, you got the right answer. Okay? So just remember, guess and check's a great idea. Also, usually remember our B to D strategy, meaning we pick D first or B first. This is probably one where you can tell if your answer for X is too big or too small just by looking at what happens when you plug it in. And remember, when that's the case, we want to try B first, because if it's too big, then I know it's A. If it's too small, I can eliminate it. And then you choose D second. That's your second guess, because if D is just right, if it works, then you got it. But if D is too big, you can know it's C. If D is too small, you know it's E. So with 2 guesses, you can narrow it down. But remember, that only works if you can tell that the number you guessed and checked with was too big or too small. If that doesn't work, then you can't use this strategy. You kind of just have to guess and check them all. All right, so let's look at an example, okay? We've got this line segment. We've got these points A, B, C, and D, and it says the ratio of AB to BC is 2 to 7, okay? Then it says that BD is 45 and that AC is 35. We want to find the length of AB. Okay, all right, so we know this ratio is 2 to 7 from AB to BC. So I'm going to call this 2x, and I'm going to call this 7x. Okay, we don't know what those x's are, but whatever it is, it's in the ratio of 2 to 7. It says BD is 45, so this length here is 45. All the way across. Now what I know then is if this segment BC is 7x, the remainder has to add up to be 45. So I know that 7x plus 45 has to equal, or excuse me, not 7x plus 45. I know that 45 is BC plus CD. Okay, well, I know that BC is 7x. So I know that 45 is just 7x plus whatever CD is. And if I subtract 7x from both sides, I get CD in terms of x. CD is just 45 minus 7x. So I can write that here, 45 minus 7x. Okay, now I know that AC is 35. So I've got AC is 35. Well, that's 2x plus 7x. That has to equal 35. Okay, so what happens is we get 9x is equal to 35. We divide both sides by 9. We get that x is equal to 35 ninths. Okay, now what are we actually being asked to find here? Looks like AB, so we plug that back in. AB is 2 times x, and x is 35 ninths. So we get 70 ninths as our answer. Okay, so you have to kind of play around with this. Now remember, this part didn't actually even help me much, but usually that will help you. I mean, you just got to kind of be creative and flexible here into setting up equations and manipulating those equations and solving the system perhaps. If you have x's and y's, remember you got to solve a system. So you got to use those elimination or substitution or graphing techniques. All right, that's all I got. Appreciate you being here, and we'll see you next week.